Hello and welcome. In this talk, I will present a new perspective on studying optimal inlining. Before we get started, let me remind everyone what inlining is. Inlining is a fundamental compiler transformation that replaces function call, like the call to bar in this case, with the bodies of calls, like the body of bar in this case. It enables optimizations by expanding a compiler's transformation and analysis scopes. However, care must be taken when deciding what and when to inline, because excessive inlining can result in binary size blowup and performance degradation. However, with proper inlining decisions, binary size can be drastically reduced. In the case of spec, we can observe an up to 3x improvement. In this paper, we focus on inlining for program size, an important optimization target as a first step to studying optimal inlining. Clearly, inlining is a very important transformation, and modern compilers use heuristics to decide what and when to inline. This is the first work that asks and answers the question of how far current heuristics are from optimal inlining for program size. But answering this question is difficult due to the combinatorial nature of inlining. Every additional call in a program results to 2x more combinations that need to be evaluated. However, as we show, this 2 to the n formulation is very pessimistic. It is possible to drastically prune the search space. In our experiments, we reduced it from an astronomical size down to something reasonable that enabled studying optimal inlining. In our study, we compare optimal inlining with LLVM's heuristic. We show that in many cases LLVM can already find the optimal, indicating that it has a very well-tuned heuristic. However, it struggles with more complex cases where there is a significant gap. We also observed a locality property that inspired an auto-tuning strategy, which we applied on spec, SQLite, and LLVM, leading to a 7, 10, and 15% size decrease. Next, I will explain how our search space reduction works. But first, I would like to explain the notation I'm using. Here we can see the same example as we saw in the beginning, where we have foo that calls bar. And we can represent this program as a call graph. A call graph has as vertices the functions, and as edges between them the function calls. So we can see here that the function foo calls another function bar. And now switching to a more complex case, we have a call graph with 6 nodes or 6 functions and 5 calls between them. So in total, there are 2 to the 5 or 32 different combinations that we would need to evaluate to find the optimum. However, we can do a case analysis here. Let's consider the call from C to D. Like with every other edge, we have 2 options, either to inline it or not to inline it. In the inlined case, C and D are merged, and there are 4 edges left, or 4 calls. And we need to evaluate all combinations of these in order to find the best one. And since there are 4 edges, we have 2 to the 4 or 16 such combinations. And for each of them, we need to run the compiler with the appropriate inlining decisions, generate the binary, and measure its size. And then we can get the best out of all the cases where CD is inlined. In the mirror case, we have a CD not inlined, and this is denoted here with a dashed and grayed out arrow. You might be tempted to think that in this case, we have again 2 to the 4 different combinations, but the main insight of our work is that, in fact, what we have here is 2 independent components. And the reason that these are independent and can be independently searched is that since we have already decided that we are never going to inline across this edge, there is no way to build the more complex inlining configurations like in here, for example, where everything is inlined. And as a result, inlining B to A cannot affect what we should do down here, since there is no way to actually combine these 2 components anymore. In fact, what we have is 2 components, each containing 2 to the 2, meaning 4 or 8 in total combinations that we need to evaluate. And once we have found the best independently on each component, what we also need is an additional evaluation to combine the 2 results, such that we can compare it with the best that we have found in the other case. In total, we have 25 combinations that we need to evaluate, which is less than the 32 the naive. At first sight, this might seem like a small reduction, given that this is a problem that grows exponentially with the number of calls in a call graph. The second insight is that this can be done recursively. If, for example, we had a larger call graph, whenever we are doing this case analysis for each edge, we can keep dividing or partitioning the call graph to smaller independent components that can be searched in parallel, leading to a drastic search space reduction. This reduced search space allowed us to exhaustively search in a large part of the SPEC 2017 benchmark suite for the optimal. We evaluated around 1,100 files. And in the median case, the naive search space size was 2 to the 8 compared to 2 to the 6 in the reduce, meaning that if we wanted to exhaustively evaluate half the files, we needed at most 2 to the 6 evaluations per file. For the 75th percentile, the reduction is even larger, from 2 to the 18 down to 2 to the 11. For the 95th, the gap grows bigger, and for the largest file, we went down from 2 to the 349 down to 2 to the 20. And it is this search space reduction that allowed us to quantify the gap between LLVM and optimal inlining. And as we showed, LLVM is already good for simpler cases, but for more complex ones, there is a significant gap. For 8.5% of the cases, there's at least a 10% size overhead, and in the maximum case, there's an almost 300% size increase. What we also evaluated is how much LLVM and the optimal inlining agree. And out of the around 15,000 inlining decisions that are included in in the files that we evaluated, in around 2/3 of the cases, LLVM and optimal inlining agree. So either they both do not inline or they both inline, whereas for a few cases, LLVM was too conservative. An example where LLVM's aggressive inlining results to a significant size increase is shown here. In this call graph, LLVM's heuristic decided to inline the highlighted edges, as shown here, and it did not inline the dashed one. In the optimally inlined version, this call graph contained no inlined edges. So this aggressive inlining results to a 69% size increase. Similarly, there were other cases where LLVM decided to inline most edges, whereas the optimally inlined versions contained only a subset or a small subset of these inlined. And having generated the optimal inlining decisions for all these files, we were able to study the distribution of inlining depth. And what we showed here is that it's mostly 1. And let me demonstrate what this means through an example. Given this call graph, an example configuration might be this one. And the notation here means for dashed edges that the call was not inlined, whereas for the highlighted ones, it means that it was inlined. What we see here is that the length of these inlined chains is in most cases is 1. So we see it in G to H or E to F or A to B. And the case where we have 2 consecutive inlined calls is more rare. So it's 3 to 1. And this is what this graph shows. Obviously, there are cases where the depth was larger, but in most cases it was very local. And this locality property inspired our parallel local autotuner for size. And the way the autotuner works can be demonstrated through this example. Here we have the same call graph that we saw before. And what the autotuner does is it selects an edge, for example, B to C, and it changes its inlining status. So if it was not inlined, it will inline it. And if it was already inlined, it will undo the inlining. And then it checks whether this results to a smaller binary size or a larger. If this experiment is positive, meaning that the binary size was shrunk, then it keeps the change, else it discards it. And then it does this in parallel for all edges and independently. So it could be run in a large parallel machine or potentially in multiple machines. And one can run the autotuner on multiple rounds, so it does this check in parallel for all edges, collects the results, and then it repeats the experiment until either convergence or for a fixed number of rounds. And the starting point can be either a clean slate, so nothing inlined, or LLVM's own decisions. So we can run LLVM, check what its inlining heuristic chose, and then use this as a starting point for the autotuner. We applied our autotuner on spec, and we observed an up to 30% size decrease for the case of MFC. We also applied it to SQLite and LLVM, as I already hinted, and the total size reduction in spec was 93%, in SQLite 90%, and on LLVM 15%. The tuning times were 16 hours, 12, and around 150 for LLVM. While for LLVM this seems a bit large, what we need to take into account is that LLVM is a very complex code base, and it also includes several auto-generated files that have extremely large call graphs with tens of thousands of calls. And these single files take a very long time to tune, since each edge results to a small experiment. Moreover, this tuning is not meant to be run frequently as part of the development process, but it makes more sense to run it before a release, such as the footprint of the target program is minimized. We also wanted to study what is the impact on performance of directly tuning for program size while disregarding the former. To do this, we used the decisions found by the autotuner, and we built the spec benchmarks and run them. And indeed, we observed that in most cases there's a slight performance decrease, and in two cases there is an around 20% performance decrease. But there is also one case, MFC, where we observed a 10% in performance increase. And this is the same benchmark that had the highest binary size reduction by 30%, which might indicate that in some cases there's a relationship or a correlation between minimizing binary size and increasing performance. And this might be an interesting direction for future work. In conclusion, this was the first work on studying optimal inlining, and it was enabled by our search space reduction insights. Our key findings show that there is a significant gap between state-of-the-art inlining heuristics and the optimal, and based on our study, we developed an effective inlining autotuning strategy. Finally, we have a way to generate large datasets with optimal inlining choices. These can be used to either improve current heuristics or maybe learn a new one. In addition, the next logical step is extending this work to studying optimal inlining for performance.